This is the ancova complete example. As you probably noticed, the last couple of videos I put up, I'm having problems with my editing and trimming part of QuickTime, and a couple of those have cut off abruptly. That's not the way I uploaded those, so something's going wacky from my editing and getting them uploaded. And I don't know what it is, so hopefully it doesn't happen on this one. So, guys, what I want to do on this one, I want to run through a complete ancova example. And remember, the goal in ancova is to examine the variation as it seems to always be, but we want to be able to parcel out the effect for the covariate. Sometimes we say we want to control for, but really we're adjusting or parceling out the effect of the covariate on our dependent variable. So in other words, we would for ancova, I want to start writing things out. I'd say we want to control for the influence of the covariate control for the influence of the covariate on the dependent variable. Actually, what I should say is we want to control for the effect that it may have on the dependent variable. Now, guys, as you're well aware, the purpose of this class is to teach you more about quantitative measures, but it's really to try to get you ready for the research sequence. And what we encounter a lot in educational research to make sure that there's no difference in entering achievement levels, we often use standardized tests as covariate. So again, the model of ancova. First of all, it's very similar to ANOVA in that we have a dependent variable that's continuous or quantitative, and we have an independent variable, a predictor, that's categorical. The ancova, or the ANOVA I should say, becomes an ancova when we add so this becomes ancova when we add a covariate. And guys, covariates can be categorical or continuous, but typically the cases that I'm, at least most ancova models I've seen, not that I've seen a lot of them, but I've seen my share, I have a covariate that's quantitative, and that's the illustration that I'm going to use for you today. Now, the two technical reasons for moving from ANOVA to ancova. In other words, the two technical reasons for including a covariate is number one, as we've talked about before, is we reduce the within group variance. Or explain more of the unexplained variance. And again, we talked about that in a previous video. And the second thing is to eliminate the confound. And guys, the confound, any study that you have, there's always a risk of a confounding variable, something that explains variation in the dependent variable but isn't included in your model, so measurements on that haven't been attained. So, and these are potential sources of bias. So. A study, it just came to me, a study that I saw some time ago, and it seems though there's some studies that have actually come out later that have contradicted the study I'm going to tell you about. But early on, there was researchers wanted to examine the effect of red wine on lowering heart disease, and it seems like some of the initial studies showed that there was a connection between the two, and it seemed like if you drank red wine in moderation versus not drinking red wine, that there was some effect, some significant effect on improving heart disease, the improvement on I guess reducing heart disease. But then a researcher came in a little later and included as a covariate socioeconomic status. And when they threw the covariate of socioeconomic status into the model, it explained a lot more of the variation in heart disease than did the drinking red wine. And it turned out what happened is it was the type of people who were drinking red wine tended to be more highly educated. They tended to be, guys, I'm pulling, it's been years since I've seen this study, but I remember it kind of well. I put it this way, I remember it well enough to feel confident enough to talk about it here. But they found out that the people who drink red wine were more highly educated and, it's a higher socioeconomic status. So it really wasn't the red wine that was kicking in, if you will, and causing, quote unquote, the reduced rates of heart disease. It was the type of people who were drinking the red wine. Now, I think recently there's been some medical research that actually has come out and even contradicted that to show that regardless that drinking red wine in moderation because of some chemicals that are found in red wine, so tend to have contributing effect on, or a significant effect, I should say, on reducing heart disease. So that's just an example. The example we're going to look at here is going to be education, for maybe obvious reasons. And what I've done here, don't take this too seriously because this is not real data. I created some random stuff. I don't know what's going to happen here because I'm kind of shooting from the hip on this one. I've worked it before. I've gone through a covariate design for this, but I don't remember what happens. So what we've got here is we've got final exam score, and these types of studies are done a lot at Shawnee State, especially in developmental math. And there's a group, and let's just say here that for the sake of discussion that the group 0 is traditional instruction. And if you come down, you'll see that we have group 1. Let's say that that's traditional instruction with the use of an online course management system. And let's say that 2 is traditional instruction with the use of an online course management system and implementing R in the statistical analysis. So again, traditional with an online course management system, something like my stat lab. And this is traditional instruction with with my math lab or my stat lab and our laboratory time. So So what they've done is, hypothetically, is we've collected final exam score. And because we want to control for the possibility that, maybe people with higher ACTs just happen to sign up for these sections, or maybe people with lower ACTs happen to sign up for these sections. Because you get into that sometimes. You get into a situation where the time the courses are offered play in more conveniently to certain majors. And certain majors tend to be a little better at mathematics than others. So it's a possibility. So going to come in and control for ACT, which is going to be our covariate. Our factor is going to be group. And our dependent variable is going to be the final exam. So gang, first thing we want to do here, obviously I should have already had this done, but bear with me, doesn't take long. And I want to import my data. I forgot what I called it. ACT 1500, okay. And let's attach it. And everybody likes to look at their data. It's a small data set, 51. So it looks like, I guess we've got, 17 in each group. So probably a balanced design. Yeah, probably it. Maybe not. Okay, well, we'll find that out in just a second. All right, guys, so first thing that I see, I'm glad I caught this. When I look at group, you and I know that these are zeros, ones, and twos. Long story short, you and I know that this stands for traditional instruction. Traditional instruction with, I think actually I said non-traditional earlier, but traditional instruction and traditional instruction with my stat lab and so on and so forth. But R doesn't see it that way. It sees zeros, absence of value, 1 being a unit and 2 being 2 units. So the first thing we got to do is we got to turn this into a factor, a categorical variable. So what I'm going to do there is I'm just going to call it factor. And I'm going to take the factor of, and let me show you something that that you can do. Anytime you're wondering if R is seeing a particular variable as a factor, you can just run what's called is factor, and it shows you false. So considering the assumptions of ancova, where we've got a quantitative dependent variable and our independent variable must be categorical, then we've got an issue here. Okay, so I'm going to just call it factor because I'm not very creative. And so now factor is going to be what I'm going to use as my independent variable, different teaching styles. And now you can see is factor, and kind of weird that we're calling a factor, but that's true. So things are good now. First thing I'd want to do is I'd want to examine side-by-side box plots. So first, we'll conduct some descriptives, if I can spell them. And first thing I'd want to do is look at a picture. So I'd probably want to examine a box plot of my quantitative. So I'd look probably at final exam, and I'd want to look at that over factor. And what am I looking for here? Measures of center, measures of spread. The medians appear fairly close, and the measures of spread, looks like there's a lot more variability in final exam over instruction 0 than there is over instruction 1. So we'll put that on our radar. Box plot, I want to go ACT over factor. And again, medians, looks like the median score for the first group is quite a bit below the median for groups 0 and 2. And again, a lot more variability in ACT scores across group 0. Again, something I'm going to want to keep in the back of my mind. Next thing I'd probably want to do is look at a histogram of final exam scores, because I need to have some reason to believe that these scores came from a normal distribution. And I'm going to look at histogram for ACT, and I don't see any major skewness, so I have no red flags there. If there are, you could possibly need to do some transformations, or you may need to run a non-parametric design. But this, with ACTs and final exam scores, I wouldn't expect it to be that way. Next thing I'd want to do is look at some numerical descriptives, and I would I'll tell you what, let me show you something new. We could do t-apply, and I could look at, for example, ACT across factor, and I could look at the means, and or I could look at the standard deviations, whatever it may be. Something that's kind of cool that we may use later on. It's we have to install a package for that. It's called statdesc. As most packages require you to choose this. I always choose the second. Yeah, it's going to be a little bit of delay depending on the computer. And guys, remember, we need to access the library for what we installed. Okay, now we're ready to do this. Something kind of cool is we can go by. I can put my quantitative variable in. Let's just go final first, because that's the one we're focusing on. And I can put my group, which I call factor, and then I can do something called statdesc. So these are just our descriptive statistics. And it brings up a mess of stuff. What it does, it looks at the final exam scores across the factor I've specified, which would be the methods of instruction. And it gives me some basic descriptive statistics: range, median, mean. It gives me a 95% confidence interval. It gives me the standard error for the mean, variance, standard deviation, so on and so forth. I could also run ACT across factor and do stat describe and get similar stuff for ACT. Now, if this isn't your thing, don't worry about it. You can just toughen it out and use t-apply and just type what you want to get. So, but anyway, that's an option. All right, gang. We got some pictures, got some plots, got some graphs for descriptive statistics, and we've got our numerical summaries. So my next step is to check assumptions. And the first thing I want to do is I want to test my assumptions for ANOVA. Now, guys, remember, ANOVA assumptions are independence, and that's checked through the design of your study, normality, and homogeneity of variance. Now, I want to check homogeneity of variance first, so I'm going to need to run Levine's test. But, as you guys probably remember, we got to install the package car. Guys, remember, installing your package, it has to be in quotations, but when we do the library, it doesn't. Now, there's something masked here, I think. Yeah, it looks like something's maybe already been loaded by the first package, and it looks like there's a little issue with some overlap with car. I'm not really sure what's going on there. But nevertheless, we could run Levine's test. And we could look at our quantitative of final over our group, which we've called factor. And I want the center to be the mean. And Levine's test for final exam score differs over groups, less than 0.05, so we have statistical significance. Raises a slight red flag, but you know, looking back at the box plots, it doesn't surprise me that there's a difference. I think we can we do by and do final and do factor and do the Levine test? Okay, maybe it needs to go factor. Okay, it's just not buying it. I'm not sure really what... Huh. No, that's not right. Okay, I'm not really sure. But anyway, well, I'll show you something that we can bypass that. Let's also go. Let's run a Levine test for ACT across our factor and center equal mean. And it looks like that the homogeneity of variances is not violated for our covariate, but it is for our dependent variable. Now, another thing we could do is we could look at the variances. So I could look at T apply for the final exam score across factor and just look at the variance. And we can use that variance times 2 trick. And the variance times 2 trick says if we take our lowest standard deviation, our lowest variance, which in this case is 141.818. And if we double that, we're going to get 282.36. If our largest variance isn't contained in there, you can see that actually neither of the two highest variances are contained. This is a good indicator of where our when we break down Levine's test of homogeneity of variance across 3 groups, where our differences actually lie. So it looks like to me it lies between group 1 and 0 and group 1 and 2. So it seems like that the variance for group 1 is significantly less than both 2 and 0. It looks like to me the major problem is with group 0. But guys, I'm going to trudge on. We could, and to test normality, we could run Shapiro as we've done before, but I'm not going to do that because the histograms looked pretty solid to me and didn't really raise a red flag. Now, what I'd like to do here is I'm going to go ahead and run the ANOVA. So I'm going to call this, I'll tell you what I'm going to do. I'm going to call it ANOVA 1 because this is going to be my first ANOVA. So I can run the ANOVA by going AOV, and my Y here is final. And I just want to run this over my factor. Okay? And what I can do now is run ANOVA of ANOVA 1. And I can see that my ANOVA is not statistically significant. Now, let me be consistent here. I think in the past we've run just a summary, and you can see we're not getting anything different. It just gives you the mean square term where the the ANOVA command doesn't appear. So this is I should never have done this up here, but I'm going to use this here in just a second for ancova. So this is the way I should have run a standard ANOVA. So guys, with the null hypothesis, mu0 equal mu1 equal mu2, and the alternative hypothesis, at least one pair of means differs. We do not have statistical significance, so we're not finding any difference in the means across teaching technique. Now, what I want to do now is I want to switch gears from ANOVA, and really everything we've done so far has just been for ANOVA. We haven't really even thought about ancova yet, because the only assumptions I've tested so far would be equal variances, and again, we could have tested Shapiro for normality, but I'm not worried about that from the histograms. But what I want to do now is switch gears to from ANOVA to ancova. And all this means is we'll now add the covariate. So we're now going to adjust the variation or partial out the effect of the covariate, or control for the influence that ACT score may have on final exam score. Okay? So first thing I'd want to do here is I want to examine the assumptions for ANOVA, ancova. Okay? And remember, those are what? A homogeneity of regression slopes and the how do I want to say this? Independence of the covariate and the teaching style, or teaching unit, which is our factor. Okay, so the very first thing I want to do is I want to do, let's do number 2 first. So first, let's examine the independence of the covariate over factor. And what we'll do there is we will, to see if these things are independent, we're going to, to see if the covariate has, let's just say it's just independent of experimental manipulation. We want to make sure that the levels of ACT are equivalent over the factors. So at the end of the day, we're just going to run an ANOVA. So I'm going to, we call the other one ANOVA 1, so I'm just going to run this ANOVA 2. But what we want to do here is we want to run the ANOVA of our covariate over the factor. And I'm going to be consistent here and just do ANOVA 2. And we don't have statistical significance. So we have no reason to believe that the means for ACT are any different over Group 1, Group 2, or Group 3. Now that should be intuitively clear why we do that. Because, for example, if we're controlling for the effect or adjusting the variation for the effect of adding the covariate to the model, if we've got one teaching style, either 0, 1, or 2, that has students with higher ACT scores, then that could be a threat. Well, it's not that it could be. It most likely would be a threat to the results of the analysis. We want independence of the covariate over the teaching unit. We don't want any difference in the means. And with the high p-value of 0.51, it appears that we don't have that. The next thing we want is we want to examine the homogeneity of regression slopes. And you're going to see an example, or well, actually, you saw an example of this, I think, in the previous video, where I go over what this looks like when it's violated. And it turns out that this is really easy to check. All you have to do is run an ANOVA and include the interaction. And really, all you got to do is just focus on the interaction, because that's all we care about here. What I would do is I'm just going to call homogeneity of regression slopes. Yeah, cool, that's fine. And I want to run an ANOVA, and I want to look at my y, which of course is final. But I want to look at this over my covariate. Interacting with the method of teaching. So summary of HOFRS. What we do here is we examine the interaction. And if we don't have statistical significance, we assume that the homogeneity of regression slopes is not violated. So we can say that since our p-value for the interaction, which is 0.865, is not higher than our threshold of 0.05, I've never figured out what's so holy about 0.05. Why not 0.049 or 0.051? But 0.05 is the industry standard, so we'll be consistent. And that's why, when we get into effect size and power, that makes things a little bit more legitimate. So since our p-value is not higher than 0.05, we can assume that the assumption of homogeneity of regression slopes is not violated. All right, gang, so it's all looking good. For us to proceed with the ancova. If there's anything right now that seems to be an issue, it's that we've slightly violated. It's kind of like slightly being pregnant, right? If it's 0.05, we slightly violated the equal variance assumption over final exam. But studies show that a slight violation in that is not a major deal. So guys, let's go ahead and run the ancova. So guys, the ancova model is just really the AOV in disguise. Actually, it's just really at the end of the day, it's just the linear model in disguise, the LM function. But so let's just go ahead and run it. I think it's reasonable to call it ancova, and we're going to run the ANOVA of our final over our factor, which is we just called it factor, didn't we? Plus the covariate, which is ACT. Now, keep in mind that, and I'll tell you what, this is worth illustrating. Let's do a summary of ANOVA. As I said, let's do a summary of ancova. Okay, and I want to show something out, point something out again. When we use ancova, let's create a second model, but let's change up the order in which we enter the covariate and the factor. And you're going to see that we get, I'm not very good at speaking and typing, you're going to see that we get different values. And then that's kind of wacky, right? And again, we got into that earlier, I think, in terms of the way that R is calculating the sum of squares. There's a sum of squares type 1, sum of squares type 2, and sum of squares type 3. Think of sum of squares type 1 as, in this case right up here, the factor has been entered into the model, and then the sum of squares for ACT is calculated on the results of adding it to the factor. So it's not dependent. I'm sorry, it's not independent. It's dependent on factor. And the same argument goes down here. ACT is thrown in the model. The factor sum of squares is calculated on the fact that ACT is already in the model. Well, guys, we want to do what's called a type 3 sum of squares calculation, where the calculation of the sum of squares is independent of anything being thrown or tossed previously in the model. A couple ways to do this. There's a drop one option, and let me just go ahead and be consistent here. Okay. So there's a drop one option where we use the model name, and I'm just going to use ancova, and then we use this tilde period, and then we have to tell it, of course, what test we're using. And when you get this, you get again the type 3 sum of squares calculation. Another way is to run what's called an ancova command in R, and I'm going to run this on the ancova 2. Now I'll tell you what, let's do it on this just to show you that nothing wacky's going on. And then all you got to do is just type equal sum of squares 3. Now when you get this, you're going to get the same thing, and I like this better for one reason. It gives us the sum of squares calculation for the residuals, for the error, which the drop one doesn't. That's important for a couple of reasons, and it's not important for a couple of reasons. The fact that when you run drop one here, the fact that your your residual sum of squares is missing is not a big deal because you've got it back here. However, it may be nice to have it in the table because we're going to use the sum of squares for the residuals in the calculation of the effect size. I'm pretty sure we use, I think we'll use the partial eta squared here, but I'll have to think about that when I get there. All right, so let's talk about what we got going on here. Let's look at the results. Again, regardless which way we ran it, we see that we get the same p-values for the factor. So what I've highlighted right here is examining the difference in final exam score across teaching method when the variability is adjusted by including ACT as a covariate. So that right there tells me that, now let me write this down. Factors p-value equal to 0.8066 tells me that a student's final let's see, let's put it this way. Tells me that the effect of the ACT is okay, guys, I'm struggling with how I'm going to put this. So the p-value tells me. All right, let's do this. So we can say that the p-value above 0.05 tells me that when the effect of ACT is removed, the effect of teaching style is not statistically significant. All right, more interesting, the covariates p-value, which is extremely small. Well, tells me that the covariate all right, having a hard time typing here, guys. Tells me that the covariate significantly predicts the dependent variable. Therefore, a student's final exam score is, yeah, let's say it this way, by their ACT. All right, so that's pretty good. That should be. Now, let's concentrate on the ancova model that we created earlier, and you know, we want to get into some post hoc stuff, and just to show you, this is kind of cool because this actually makes you think about regression, and again, regression and ANOVA and ANCOVA very, very closely related. If we use what's called summary.lm of our ANCOVA model, it's supposed to create, it creates dummies. So what a dummy variable, if you remember back from Math 5500, when we have, wow, we've been doing a lot of stuff, haven't we? When this is, when we have a predictor that has more than two groups, that's categorical and has more than two groups, it will choose the first as the dummy, the reference group, and then it will compare the means to that particular group. So that's what this function, the summary.lm of our ANCOVA model, has done. This factor 1 compares teaching group 1 to teaching group 2. I'm sorry, teaching group 1 to teaching group 0. And this factor 2 compares teaching group 2 to teaching group 0. Nevertheless, when we break this down, we see that the only significance that we have here is in the covariate or the ACT. So if somebody was hoping for something that one of these three teaching techniques seems to be more effective than the other, it doesn't seem to be. Now let me tell you what people who know squat nothing about statistics will do. And trust me, this happens a lot. This happens a lot even in our math department. I could look at final over factor and just look at the mean. Now, if you want to do some stupid statistics, pull this one off. Because the mean final exam score for group 2 is 74.8, which is higher than the final exam score for group 0. Now, people who know squat nothing about statistics will take that and run with it and say, well, we all know that the teaching group, the teaching approach number 2 is better because these students scored higher. What they're not appreciating is the fact that samples vary. This is just one sample of infinitely many. And when we want to make generalizations as better to the population for which we're trying to generalize to, we have to let inference procedures play its way out. So we would run an ANOVA, and if we can make the case for, and I think we could in this situation where the ACT math subscore should be included as a covariate, we run the covariate. It actually turns out that there's no difference, and really the best predictor of the final exam score is the ACT score. The teaching approach 0, 1, and 2 seems to be irrelevant. All right, gang, the post-talk is going to be anticlimactic here. It's not going to be very exciting because we didn't find statistical significance. But nevertheless, we would want to be able to run a post-talk. So let me show you how to do that. We're going to use what's called a GLHT command. But to do that, we've got to download a package, install a package called multcomp. So we're going to install another package. Remember, when we install, we have to put in parentheses And I think it's multi-comp or multi-comp. I don't remember. Let's see what happens. Okay, must be multi-comp, so I lucked out. So guys, remember library, we don't put in quotations. So it's loaded, and MTV norm, I think, is the one that we need. All right, guys, so what I want to run here is just post hoc. And I use what's called the glht command. And I want to run this on my ancova. And I want to run my linear, fact CT. All right, guys, I don't know if it's LINFCT or LINFACT. I guess we'll find out, right? All right, cool, I lucked out. So guys, what I can do to run my, to look at the differences in terms of p-values is I can run the summary of post hocs. And again, what this does is it gives me comparisons of group 0 to 1, 0 to 2, and 1 to 2. So it makes all the multiple comparisons, controlling for adjusting the variation in final exam by including ACT as a covariate. And again, just as you would expect, since our factor wasn't statistically significant, we're not finding statistical significance there. Something else that's kind of cool is the confidence interval. You know, if there is statistical significance, this gives you the upper and lower bound. And you can see that the lower and upper bounds contain 0, which says that we do not have statistical significance, which you know, correspond to what our p-values say up here. Okay. And the more symmetry you get around 0, you'll have higher p-values up here. For example, if we ever get a p, let me put this down here. If you were to get a p-value equal to 1, then your confidence interval would look something like a -2 to 2. So the more symmetry you get around 0, the higher that the p-value is going to be. Okay, that's just kind of some extra stuff. Now, what I want to do now is I want to go back to the Blackboard. So give me a second. All right, let's connect. For some reason it's not wanting to connect. All right, there it goes. Well, that was weird. Okay, when we get into effect size, what I want you to use is called the it looks like a new, looks like an N, but it's called partial eta squared. And partial eta squared is just the sum of squares for the effect over the sum of squares for the effect plus the sum of squares for the residual. And we're going to want to create this for both. So again, this eta squared is the sum of squares for the effect over the sum of squares for the effect plus the sum of squares for the regression. And we will want to do this for our covariate. And we'll want to do this for our treatment. Now, this is a situation where it's kind of, you know, where we had that drop one a while ago where we did our type 3 sum squares. And I showed you the other way using the capital A, lowercase nova. This is a place where, yeah, let's go to R. Okay, this is cool. It's not letting me get to R. All right, so when we go back up to, gotta be careful here. I want the, okay, right here. When we go back up to the capital A, NOV, this, what we're going to have, and I'm going to write on the blackboard, and then we'll go back to it in just a second. For the covariate, the sum of squares for the effect is going to be 8538.3. And of course, this is going to be over 8538.3 plus for the residuals, which was 4027.1. And then for the treatment, that will be under factors, so that's going to be 37.0 plus 37 plus 4027.1. All right, so let's go down here and get this. So the effect for the covariate is going to be 8538.3. 8538.3 plus 4027.1. So the effect for the covariate is 0.68. And effect for the treatment is 37. Don't know why I named it that big. So 0.09, so very, very, very small effect for treatment. So yeah, it kind of makes sense because of the results that we found. Now let's go into Gpower and let's calculate. I should have that up. So if we go to Gpower, and what I want to do is I'll want F-test, and I want ancova, which we want the fixed effects. Oh, so cool, it's already there. And what I want to do here is I want to calculate the post hoc, compute the achieved power. Now, when we come to our, well, this is not good. Okay. It requires effect size F, but we didn't do effect size F. We did partial eta squared. All right, let's see. How about this? Okay, this is exactly what we need here. Let's calculate the power for the covariate first. So the partial eta squared for the covariate, darn it, I didn't write that down, was 0.6795. So I'll calculate and transfer. Okay, I see what happened. It calculated, wow, cool, all right. 0.05, our total sample size is 51. the numerator in the degrees of freedom. That would be the numerator in the degrees of freedom, or the degrees of freedom in the numerator would be would be 2. No, wait a minute, that's not right. The degrees of freedom for the numerator would be 3. And the number of groups were 3. And the number of covariates is equal to 1. So, tons of power. Now, let's come over here. I think this was 0.009, if I remember correctly. And let's calculate. And very low power. Guys, I have to confess to you, I'm not sure that this numerator degrees of freedom is correct. So I'll tell you what let's do. Let's just go see about it. Okay, let's. This is actually something good for you guys to have on your radar. So let's do a degrees of freedom numerator for ancova and see what we get. A page that is okay, so okay. Yeah, sorry about this. I wasn't expecting. Okay, let's see. Here we go. Okay. So it looks like factor B has 3 levels. Thus, the test of the main effect on factor B has okay, so they're doing a 2x3 design. The covariate has been partialed out. The dependent variable, we want a large effect according to the conversion for factor B. So a 2x3 design. Okay, the denominator degrees of freedom, because denominator degrees of freedom are n minus the number of groups. Okay, I had that one. That's not a problem. The numerator degrees of freedom is n minus, so the number of levels minus. Okay, guys, I screwed up there. When we go back to 0.6795, so let's do this the right way. Our degrees of freedom, since we had 3 teaching techniques, our degrees of freedom should be equal to 2. And okay, so our power is 0.084, so we have extremely low power here. I gotta admit, I'm kind of shocked by that. I was gonna look that one up. I know the way that F statistic is calculated, and the degrees of freedom for the numerator being 2 isn't meshing with me right now. Let's see what happens up here. Variance explained by the special effect and the error variance. Well, the variance from the special effect, this might be the best way to do it. For the covariate is 85, 38.3, and the error variance is for 027.1. Degrees of freedom, yeah. It's still going to give us a power of 1, yeah. All right, gang. Until told otherwise, we will use the numerator degrees of freedom being the number of groups in our independent variable minus 1. So we have 3, and obviously we get numerator degrees of freedom equal to 2. All right, so we're going to go with that. Sorry for the confusion there. And I think really it's easiest probably to just do it from the variances. But do whatever turns you on there. Just go for it. Again, sorry for the confusion there. But this part right here threw me a curveball. But again, let's go with number of groups minus 1. All right, guys, that's all I got. Again, sorry for the confusion there at the end, but those things happen. If it was in a classroom, it wouldn't be that big a deal, but it just seems clumsier when it's on video. So sorry about that. Take care.